All right. So good morning again. So let's just walk through the website just to remind you of, where everything is. So I'll share my screen. Okay. So this is the home page. So please, I would just like to remind you that this is the grading scheme, and yeah, please be in touch with us, and in particular with Philip regarding the lab assignments, because there's a lot of points that you can get there, and that you should submit everything on time, because the big assignments are mandatory anyway, and if you fail to submit on time, you will get a penalty. So you will have to work, but you will lose the points. So yeah, I really advise you to do the work regularly and on time, and talk to Philip ahead of time, such that you can get these points, because that's a lot of points, basically almost half of the points for the whole course. So at the end of the term, you will be very happy if you have scored well there. As part of the lectures, so we are here now, we're running online. That's probably not going to change very soon. So we are here, we're doing the Expectimax today. So I asked you to watch this video from Berkeley, which is this one, and there's quite a big overlap with the content of today. So I assume that you have watched the video, and that basically you can come up with questions, and we just so we do a short lecture, but we can make it more interactive if you have any queries and feedback. And we're going to continue doing it this way, at least for the next 2 lectures, where we will move to decision making under uncertainty, Markov decision processes, and again, I already put there links for you to watch from the Berkeley course. So this course is really good. Both Dan Klein and Peter Abil are really top scientists, and yeah, I think it's done really well. So this is the overview, and yeah, today and then the next 2 lectures, basically the scheme will be that you are asked to watch this prior to the lecture. We do a short lecture, but I'm here for questions, and we can make it more interactive if you have any specific things you didn't understand. Okay. So I guess that's so much for the web page, and I can stop the sharing the screen. So if you have questions at this point regarding this lecture here, then you can put it in the chat, or you can speak as you prefer. Okay, so otherwise I will start my slides, which, by the way, I just uploaded here, and we will briefly go through them. Okay, so let's make the slides bigger, and let's walk through them. So the general idea is that as we go through the course, we're introducing more and more complexity. So we started with search, where basically it was only us picking, let's say, the best path. Then we introduced the opponent, so games. So that was the Minimax, which of course made it more difficult because it was not all under our control. Nonetheless, we could still make a sort of convenient assumption that the adversary, the opponent, is a rational and a sort of perfect opponent that is also maximizing his utility. And that allowed us to sort of search more efficiently because of this Minimax algorithm and alpha beta pruning. And today we're going to introduce another level of complexity, which is chance or stochasticity. So computationally speaking, this will make matters even worse, because you cannot assume any strategy. You just have to basically toss a coin or roll a die, and that in terms of how the search space blows up is much worse than actually a rational perfect opponent. So that's the idea what we're covering now. So yeah, just to recap, that was the minimax. Let's say I'm player A, I'm maximizing. On this level, there's the min player, but he's minimizing. So for him, the smallest numbers are the best. So he would pick a 3 here, pick a 2 here, pick a 2 here. But I'm maxing, so I will take the biggest and put it up here. Okay, so that's fairly simple. Okay, now imagine we replace the min player with chance nodes. So that means it's not up to any rational decision, it's up to randomness, up to chance. So they are not actions. Okay, good question. Thanks. Stochastic environment. Stochastic is a technical term, let's say from probability theory or from statistics. That means that it's not. So the opposite of stochastic is deterministic. That means I choose to, let's say, do action A and it will happen. Stochastic means that it's subject to chance, subject to randomness, that there is a probability distribution. Okay, so stochastic means with chance, with randomness. It's just a technical term, but yeah, but there's nothing more than that. Okay. Okay, wonderful. So here they are not actions that somebody can choose, but they are outcomes of chance. Okay, so imagine you roll a die. So in that case, they are sort of not real actions, but they are they are basically outcomes of chance. So and so the idea is that we want to sort of bring all these algorithms closer to the real world, and in the real world, as you can imagine, the real world, at least from the perspective, say, of a robot, is stochastic, because it can really, it can choose a certain sequence of actions. It can plan to go somewhere, but it will hardly happen exactly in that way, because there is noise in perception, in the sensors, and also on the action. So, it may well plan to sort of, move the flipper by a certain, number of degrees, and then think that it's going to be beyond this obstacle. But in reality, this may not be exactly the case, because there might be some slippage. So you would be, spinning your motor, but in reality, you will not move, and then, then everything will change. So basically, in the real world, you need to deal with, let's say, stochastic environments and with uncertainty. So the motivation. So this is an example how we can look at a tree that has some chance nodes. So imagine you want to go from home to work, and you have 3 options. You take a tram, you take a bike, or you take a car. So you're sort of, you're the max player still, so you can choose, which one. But now the chance nodes in this case for the tram, it's going to be, let's say, the situation on the rails. So and this is the time it takes you to get to work. So if the rails are free, it will take you only 3 minutes. If there is a traffic jam, it will take you 8 minutes. And if there is an accident, it's going to take you 12 minutes. Okay. Something similar would be for the bike and for the car, but this is not going to be the situation on the rails, but it's going to be something else. I don't know, like, whether it's raining or something like that, or whether you can find parking in case of the car. And but this in this case, this is not, it's not your opponent, the environment. It's just subject to something that is out of your control. So these are basically, in that case, chance nodes. So if you so in Minimax, we knew what to do, right? We would sort of, in this case, let's say, if the world was against us, it would always choose the biggest number, because it would take us the longest time to get to work. But if this is not the case, how can we combine these numbers? Do you have an idea how to assign the value to this node and this and this? What are the possibilities? What are the options? Take average. Yeah. Okay. That's a very good guess. We could take an average. Other options. So, yeah, I mean, unless I know anything more, taking an average is a good alternative. We will learn that we can do sort of even better if we take if we have extra information. We could also take the worst case, you know, if you really need to be sure you are on time because there is an exam or something, and that would basically lead us back to the minimax. That would be sort of, you know, if I really want to take the worst case, then it's going to be as if the world was playing against me. So yeah, so average case, not the worst case. And what we want to calculate is basically expected utilities. And so the average is going to be the optimal approach if all these events are equally likely, or if we don't know how likely they are. But if we have extra information, such as, you know, there's always a traffic jam, or, you know, the accident is probably not happening every day, then we can do better by taking a weighted average, weighted by the probabilities of those particular events. Okay, so that's the weighted average expectation of the successors. And this is the way of writing the pseudocode of the algorithm. So we were used to minimax. This is going to be very similar. So for every state, we want to return its value, and, you know, it's a recursive algorithm working down the tree. It's a terminal state, then it has a utility. Otherwise, if it's the max level, then I'm gonna, you know, want the max value of the state. But if it's the chance level of the tree, then it's going to be the expected value, not the maximum value. This is for the max. We know how this works. So we assign minus negative infinity, and then we max over the actions, over the expected, over the, you know, values of the nodes below in the tree. But here, because the next let's unfold also this one. So the difference between the max value and the exp value is that here I'm maximizing. So I will basically take the value of one of the nodes, the one that is the best for me. While in the exp value, it's gonna be this average, which is weighted by the probabilities. So there are random events R. Each of them has a probability. So the total value there is going to be a weighted sum of the values of the chance nodes. And here I'm initializing to 0, right? Not to minus infinity, because, you know, I'm just making a weighted average of the outcomes. Yeah, so, you know, so this is really basics of probability theory. We don't really need, you know, anything sophisticated, but I assume that you are familiar with the basics of probability theory. So in this case, the random variable is the situation on rails, and the outcomes events is these three possibilities. And this is the probability distribution, that this capital R can take up three values: free rails or accident or congestion, and they have these different probabilities assigned to them. Yeah, you know, there are basic rules of probability. Yeah, always non-negative, sum, etc. Right. So how long does it take to go to work by tram? Depends on that variable R. So what is the expectation of time? This, yeah, we already alluded to, you know, what this might be. So it's going to be this weighted average, the probability of the individual events. And in this case, it's the time. So in this case, the evaluation, the utility, the value is the time. So you just do weighted average, and you will get the, you know, weighted average of the time. So that's pretty intuitive. Okay. Yeah. How about the reverse game? So, is there any space for randomness? So, I mean, it's a game like any sort of any other typical game. So there's no, you know, no explicit element of randomness, but it kind of course, depends who you're playing against. So, you know, you can also play against a random opponent. I think I also tried on the internet. The game actually is not so simple. So, you know, even beating a random opponent in this case is not that easy. So if you have extra information, you could consider it. Two notions, you know, that were also discussed in the lecture from UC Berkeley is dangerous optimism and dangerous pessimism. So if you're, you know, assuming that everything is random while the world is actually, you know, going out to get you when it's adversarial, this is called dangerous optimism. So in games like, let's say, chess, it doesn't really pay off, you know, this dangerous optimism. It can really be dangerous. So even if you know that your opponent is maybe not, you know, at the same level as you are, assuming that he's a fool and that he will overlook something is dangerous, right? Because he might surprise you and he might lose. So in games like this, that when, you know, there is a single outcome at the end, there is no real reason why you should, you know, you should do that, why you should assume your opponent is a fool. So you should still play, you should still assume that he's the perfect opponent, and, you know, that's going to give you the best results, because there's no cost, you know, for, you know, that the game is taking long or something. So in that case, you know, you have no reason to do that. But there are other games, like, for example, the Pac-Man that was in the Berkeley lecture, where you have also cost associated with every move. And so, you know, if you assume the ghost is your adversary and it's behaving optimally, while in fact it is not, you saw that example that, you know, it costs you unnecessary time waiting for the ghost to go away, while you could have just went for the target straight because the ghost was in fact behaving randomly. So, you know, depends on the context. And, you know, dangerous, that was a dangerous pessimism is the opposite notion, that, you know, that was for that Pac-Man example, that you're assuming, you know, it's a perfect opponent, while in reality it was random. So yeah, so these two notions are important. And yeah, so this game, so backgammon is a game where we really have all these three things together. So it's a sort of combination of minimax and expectimax, because there is your opponent. So I don't know how to play this game. Okay, so you're somehow, as the white, you're supposed to move your move in this region, and the opponent in the opposite region. But every move that you roll these two dice, and based on that you can basically it determines which moves you can make. Okay, so there are all these three factors in the same game. And so it looks like this when you unfold the tree. So here is the max node, here are the chance nodes, and here you see the probability. So this, you're rolling two dice. You have to get a 1 on each of them, you know, to get in this 1-1. So there's 1/36, because there are 6 times 6, 36 combinations. To get the 1 and the 2, you know, that it's only 1/18, because you can get the 1 on the one die and 2 on the other, or the other way around. So it's 1/18, and the same for other combinations. And then then there's the min player. So basically it looks like this. And then there are some terminal utilities. And you see that there is quite an explosion of the states, right? Because there's, rolling 2 dice is, blows up the tree quite a bit. So it's going to be, more difficult to compute, and it's going to be, basically hopeless to compute till the end. So this is, what we saw before. So this would be expected minimax, because it's, as I said, the combination of expected max and minimax. So the utility of the terminal, that's the simplest, that's the leaves, that's the terminal. And then if it's the max player, then it's going to be maxing over actions from that node. If it's the min player, it's going to be the min. And if it's the chance, it's going to be this weighted sum, weighted by the probabilities of the different events. So if player is chance, so you can imagine the chance levels of the tree as if there was another player, the chance player. Right. Now, so how big is the tree going to be? Do you have any guesses? So we had some expressions in terms of, let's say, time complexity for the for minimax. So let's. So for minimax, we had something like O B to the power of M. So this was the time complexity. So B is the branching factor, and M was the depth of the tree. So what is going to happen here? So I still have to practice with this tablet. So let me try to write this a bit neater. N times B to the power of M. Okay, B to the power of N. Okay, so we see different options in the chat. B to the power of N times M. Interesting. Okay. Well, okay. None of them is still right. Maybe Elisa wants to say something. B and okay, that's good. That's yeah, it's not easy. Okay. Okay, so I'll write the answer and we can have a look. So in this case, it's B to the M times N to the M. And so let's see why it is like that. So you can also imagine it as sort of two different trees, one dealing with the minimax, which is the B to the M. So it has a depth M, and branching factor B, because these are the number of moves you can make if you're either the max player or the min player. So that we know. And then interleaved with that is sort of another tree where the branching factor is different. The branching factor is N, because that's the outcomes on the on the dice, how many outcomes are on the dice. And it has the same depth just because there is a chance level, after every max and after every min. Okay, so basically it's going to work like that. And the M is the same because, because as I said, it's basically for every layer of the original minimax, there is a chance layer. Okay. If the rolling the dice was not happening as often, then there would be, a different letter here that is basically this would have a different depth. Or there's also other ways of sort of interpreting this, but basically this is the correct answer. So you can also view it as that every rolling of the dice sort of multiplies the number of trees, right? If there was just one roll of a dice, then you would have to consider n minimax trees. But since this is happening always, at every level, then it basically is like that. Okay, so this is, it is a bit tricky. Okay, this is one additional property, which is that for minimax, only the ordering of the terminal values basically mattered for how you navigate through the tree, how you basically choose the optimal action both for the min and for the max. However, with the Expectimax, since it's the weighted average, it's not just the ordering, it's the actual values that matter. So here you have basically a counterexample. So everything is the same. The only thing that happened here is that you left this 1 intact, you multiplied these by 10, and you multiplied these 4s by 100. And suddenly, the action to choose will be different. Okay, so let's look at it. So this is the min layer. I'm going to choose a 2. This is the same. Well, there's 2. Anyways, there's nothing else to choose. And here are the probabilities. So I'm going to make this weighted average. So 0.9 times 2 plus 0.1 times 3 is going to give me 2.1. I do some similar calculation here. And I'm going to choose the A1 action as the max player. 2.1 is bigger than 1.3. But if I do this, operation on the terminal values, it's going to come out different. Because this 400, despite the fact that it's only 0.1, is going to, influence the evaluation here, and I will eventually choose A2. And so this is, so that means that every value sort of matters, which of course will have consequences for the how much or whether at all we can prune the tree, because if it's really like that every value matters, then there's nothing we can prune, right? Because if there is a huge number weighting, and it's going to be part of a weighting every weighted average, if it can be really, really huge out of our control, then we will just have to see it, because we will not be able to say, well, I don't need to see that because no matter what is there, I don't care. So that's changing. So it turns out that if the operation you do on these terminal utilities is linear, then basically it's gonna preserve the state in terms of which actions are going to be optimal. But this was not a linear operation. What happened here, and then this may change basically the outcomes. So yeah, so the actual scale, the actual values matter, not just the order. Okay, so regarding the pruning, so let's look at an example. So the point is that for you to be able to do pruning of the Expectimax or Expectiminimax tree, the minimal values need to be bounded. So we saw that, because if they are not bounded and they are part of this weighted average, you can blow up something almost to infinity, and it's eventually gonna change the situation. But if the values are bounded, then you can still do some pruning, because you know that it cannot go beyond something, even if it takes part of that weighted average. So here is an example of a tree. So try to guess for a little bit what do you think can be pruned here. So this is the max player, these are chance nodes, these are the probabilities, and then there is the min player. Here you have 4 different examples what one could prune. So I'll do a poll, and it will take you a bit of time to work through that. So A, B, C, D. You can assume that you will be, starting from left to right, basically, like we always do. Okay, so let me publish the results. So the correct answer is actually C. So I admit that this is tricky. So let's work through that. So let's start from left to right. And so first we evaluate here, right? So this is a min thing, so that's easy. So that's going to be a 2. Okay, let's move on here. This is going to be 1. That's clear. Now it's going to be weighted average, giving us 1.5. Okay, so far it's easy. So we sort of bring this up, this 1.5. And, we cannot write 1.5 here yet, but what we know that is, similar sort of to the alpha beta pruning idea, that for this part of the tree to be chosen by the max player, it would have to give us basically 1.5 or better. Okay, so let's have a look. Let's start here, but here is a 0, and so now the trick is that even if I don't know what here is, I know that this is going to be, so it's bounded from -2 to 2. So for, let's say, I'm putting on the head of the max player. So even if there was a 2, but I'm not seeing it yet. 0 and 2. So basically, so the min player is gonna choose I got a little bit confused. So from 0 and 2, the mixed min player would choose the 0, right? But if there was, say, a -1 or -2, it would get even worse. The point here is that if there was anything worse than a 0, then half of it would be something negative. Okay. And then here the maximum I can get without looking, if they were 2 and 2, min player would have to choose 2, and 1/2 of it would be a 1. So if I get something negative here, and I get half of 2 here, which is 1, I will not be at 1.5 or better. So basically, I don't need to look here, because if there was anything worse than 0, I know that I will, as a max player, I don't need to look any further. So that's one thing. And the same applies basically here, because now that I have this 0 or worse here, no matter what is here, if the best I can get would be 2, 2, and 1/2 of it is 1. So I don't have to look here either, because so really getting 1.5 would be the would be the best I can get, but most likely it's going to get worse if so basically I can take a shortcut in this way. Okay, so I know that I have to get 1.5, right? And here I have a 0 or worse, so that's a 0 or worse. And here I have a half of whatever is down there, which is going to be at most 2. So this is going to be at most 1, the value is going to be at most 1, and here it's going to be 0 or worse. So I already know that I cannot get 1.5, so I can prune like this. It's not as straightforward as with the alpha beta, but it is possible in this way. Was it clear? Can you explain why B was wrong? Okay, why B is okay. So let's see. So B, so B, okay, let's take a different number. Different color. So B was, would cut it off here. Well, I cannot just cut it off there, because if I have 2s all over the place, it would just end up being a 2, right? And I cannot do that, right? Because, I would lose the better opportunity. So I cannot just cut it off here. So that's not possible. So I really have to go here down. Yes, we can only, exactly, we can only prune because we have those bounds. How do we establish them? Well, depends on the context. You have to know that you cannot establish them. In this case, it's part of the rules of the game, right? That they are bounded. And yeah, you cannot find out. I mean, you can sort of try and then make a sort of heuristics, but in this case, it's given to you. It's like that. Right. So we cannot prune here, but we have to look. We have to look, and we have to look here. And now the key thing is that we saw this 0, and from there we can already make this this inference. So we have a 0, and so that means that that here it's going to be smaller or equal to 1, right? Because it can be, if there is a 2, it's going to be 1. If there is something less than a 2, wait, no, I also got lost myself now. So okay, so so this is the min pair. He's gonna choose a 0. So this thing is gonna be 0 or less. Okay, and then this is gonna be weighted here. So it's gonna give up a 0 or less. And then even if I had a 2 and a 2 here, this is gonna give me only 1. So this is the value up here. So basically, you want to know what is going to be here. And from here, the contribution of this branch is going to be maximum 0. The contribution of this branch is going to be maximum 1, because it's a 1/2 of 2 if there were 2 2s here. And that's basically it. Now it's never going to give you 1.5, so you don't need to look any further. If you look here, it can only get worse. If you look here, it's actually going to get worse because there are not 2 2s. It's going to, in the end, be much less than that. So that's basically that's the point. So it's enough to just see this 1 0 to know that you're never going to get 1.5 up, and that means you can stop looking. Yeah? Okay. Things can get even more complicated. There can be, multiplayer games, and the complication is that basically they have, each of them would be maximizing their utility, but that will also have effect on the utilities of the other players, meaning that there could be, coalitions, cooperations, competitions. So this is quite hard, and we will not, tackle these kind of games in our course. So just as a recap, so we're heading toward the sort of real world where the actions of robots or agents have uncertain effects, and where also eventually we will learn that the perception is loaded with uncertainty. The robot may not know the current state. Okay, it's not so the technical term is that it's not directly observable. It can have observations from its sensors, but the state, such as the state, it's at the edge of a cliff, is not directly observable by the robot. Yeah, uncertain outcomes of actions. So observations E, this is what the sensory readings are. Uncertain outcome, random variable, result of an action A. And yeah, S prime would be the next state if you have observations. So you don't have direct access to S, which is your current state, but you have the observations and you have an action that you can take, and the result would be a state S prime. There will be a utility function, and then this expected utility is basically the generalization of what we discussed. So you're summing up over the future states that can result, from your current observation and action. So this is the expected utility of an action given the observation, so the sensory readings. So obviously a rational agent should maximize that utility, but in practice the problem is that the variables that you need to compute that are basically hard to get, and this is what we will look into in more detail in the rest of the course. And so the final part is about the utilities, and this is really basically the same what was in the Berkeley video. So I'm not going to go through that. Okay, so yeah. So if you have not watched it already, please watch it. And it's about lotteries. It's about rational preferences. They have to have some properties such that they can be declared rational, and such that basically all the maths can work out. So axioms of utility theory. It's about turning preferences into utilities. So preferences is I prefer something over something else. That you can also ask people, what do they prefer? But utility is actually a function, so it's a formalization of the preferences. And if the preferences are rational, if they fulfill these axioms, then some things hold. So for example, you can find a utility function. This I think we don't need to go through, and it's explained in the lecture from Berkeley. This is the utility of money. And there we are. Questions? Is pruning really required if time is not a factor? No, I mean that's a good question. Time or space, right? So there is this time complexity and space complexity of the algorithms. If you have unlimited time and unlimited memory, you don't need to do pruning. But the fact is that in pretty much all, sort of real situations, or in most games, you just cannot afford to compute till the end, unless it's a sort of trivial game like the 3x3 tic-tac-toe. So, and so with the chance node, so with Expectimax, you saw that the complexity of the the explosion of the tree is even more dramatic. So, for example, in the backgammon, you can only count to depth 2, which is really shallow. So, so pruning, if it helps you to get a bit further, you can get much better. So it's not really required if time is not a factor, no, but in practice it can, it can save you precious time, and you can compute more deep, and that's going to improve your performance. It's basically as simple as that. And remember that, for example, for the alpha beta pruning, you can save up to half of the time, basically, depending on circumstances and how you also order your nodes. But so that means you can compute twice as deep, and that's going to make a huge difference. I still do not understand why we can prune the number 2 in option C on slide 17. It can be even lower, which would affect the node on the right. Okay, let's have a look. Okay, going back. Right. why we can prune the number 2. It can be even lower, which would affect the node on the right. So the point is that we're taking it from the perspective of the max player. So if this is even lower, so let's say there is, let's say there is a -2 here. Then, this would become a -2. So the point is that, so for this part of the tree to be interesting for the max player, it has to give at least 1.5. The only way, like here, that you can get to 1.5 is that there has to be a 2 and 2 and 1 and 2. Right, or I mean, so there has to be, one has to be 2 and one has to be 1, or both have to be 2, right? Now, if you already know that this one is 0 or worse, even if this other branch will contribute a 2, you're just going to end up with a maximum of 1. So basically seeing this 0, the point is you cannot sort of do this locally here, but you have to take into account also the other branch and how much it can contribute. So it's, in that sense, the alpha pruning was easier because it was sort of acting more locally. You could directly compare with the alpha or beta here and say, I'm going to look or I'm not going to look. But in this case, you can prune. It's more complicated because you have to take this whole thing into account. If there was an extra branch here, it would not work like that, right? But because there is just one more branch that can contribute at a maximum 1, seeing the 0 allows you to cut the rest off. Okay. Other questions? And I'm going to upload another version of the slides that has notes. And in those notes, you have a worked out example of this. So you can also have a look there. So it will appear just after the lecture as an extra PDF on the lectures webpage. Okay. So it seems there are no further questions. So then I would thank you for your attention. And yeah, please remember that for next time, it's the same scheme. Please have a look at the Berkeley lecture before. If you come with specific questions, that's perfect. And then we can make it sort of more interactive and you can profit more from this online lecture. All right. Okay, thank you very much and have a good week, and yeah, enjoy the lab with Philip this afternoon.